My name is Justas. On behalf of my colleagues, I'll be presenting real-time data visualization in the Adaptive City platform. So we started working on the Adaptive City platform a couple of years back, where our initial goal was to create a system that would enable to ingest data from building information models, building management systems, and IoT data. The goal was to create this asynchronous real-time system for sensor collection that would combine all these resources into a single unified platform. However, for the purposes of this demo paper, we'll be dropping the BMS bit. I'll be mostly focusing on the BIM and IoT interoperability. Our first starting point was to buy a bunch of sensors and then connect them to our real-time asynchronous platform. We bought over 300 of ELSYS sensors capable of sensing temperature, CO2, and humidity, as well as some capable of having read switches for open-closed door sensors. All of these sensors have been installed across the 3 floors in our department building. As you can see, this is our system architecture. We're mostly using LoRaWAN sensors with TTN backhaul. Of course, the core of the platform is the data layer, where we have our Java-based Vertex platform capable of ingesting all of the sensor data and passing it through the platform with minimal latency. On our application layer side, we're using MQTT mechanisms with WebSockets to ingest all this sensor data and just pass it through the platform without having to rely on data querying from data repositories. So initially, below the web page, we query the data for BIM information, and then we open WebSockets so that the sensor data can just flow through. And the average data propagation time is measured in hundreds of milliseconds. Now, since this is a talk on a demo side of the platform, I'll be mostly showing you the browser interface of how the users actually interact with the platform itself. So here you can see this is our landing page. We have a bunch of cards, and for the purpose of this talk, we'll be mostly focusing on the space part of the platform. That is the data visualization section, where we're gonna go through the site overview, BIM floor plan, heat maps, and chart templates that we've created for the platform. Other important cards include the sensors card that has all the information on the collected sensor data and sensors metadata, and then the data management section that we use to edit our collected data on BIM and sensors, including metadata that we can edit and change if needed. So you can see in the demo paper, there's going to be a link with an in-depth analysis of what all these different cards do, so please consider having a look at that. Now, if you click on the space card on the landing page, you're immediately taken to the site overview or the map view of where different smart buildings deployments have been made in Cambridge. Upon clicking on the desired building, you're taken to a building page, and then from there you can select the floor that you're interested in, and then be taken to the view that you can see on the right. That is the rendered floor plan view with a bunch of sensors represented as circles. Now, if you hover your mouse over one of these circles, you can see a tooltip appear with the most recent snapshot of the readings for that particular sensor. And in this case, we have an ELSYS eye sensor that comes equipped with a 8x8 infrared camera. And here we can see a snapshot of that camera appearing in real time upon request from the browser. Now, if you click on that sensor, you can be taken to see time series chart views for more in-depth analysis of what the data actually means and how it correlates with different values. For example, it might be interesting to compare CO2 values with temperature values in a given room. But now the key points that I wanted to focus is going to be how we get our BIM and floor plan information on the front-end user interface of the platform, and how we use heat maps to better explain the data. So here, I'll quickly explain what's happening. We have our floor or building data acquisition step, where we take our BIM models or SVG models, we parse them, and then using some ontology of our choice, we create a virtual building representation in form of building database. Then we use that building database to connect it to some API requests coming from the front-end user interface, where we, based on that building database, database information that we have, we generate building SVGs and then pass it on to the front-end interface. Then we draw everything using the 3JS, including the generated SVG file and all of the sensor information. Now, to learn more about the process, please consider reading some of the papers that we've referenced below. Now, the core problem of visualizing this BIM and IoT fusion is that we don't really use a lot of space that is provided by our building floor plans. So, for example, here you can see some of the more popular examples of what's being done on different platforms. So here we have a floor plan with a bunch of sensors represented as circles, which is perfectly fine. However, these sensors show different colors and values, but it's quite hard to understand a more general view of what's happening on the floor plan. There's a lot of empty space, and your mind kind of has to interpolate what's happening in between these sensors. Another option is to use choropleth maps, where you can average out different values from readings in a single room and then color it based on those average values. Now, the problem with that is that if we have a really long corridor, one sensor at the one end of the corridor is going to have one value, and a different sensor on the other end of the corridor is going to have different values. And then if we averaged it out, we lose a lot of fine granularity that would have been available otherwise. Now, the final solution to this is to draw a heat map, right? Now, the problem with heat maps is that some rooms in our buildings are just cooler or warmer, depending on their purposes. For example, server room would have a different temperature than one of the offices. And then what happens is with this type of application is that, for example, temperatures will start appearing to leak on this virtual heat map, therefore giving kind of wrong information of what the actual temperature in different offices is supposed to look like. So you can see a generalized view of these three problems, and I have references for each of them below. Now, our solution was to use heat maps. However, we have room-constrained heat maps, where we take our physical wall properties of different rooms, right, and we kind of elevate it to a virtual space where each of these heat maps are limited by hard wall boundaries. And therefore, what we have is room-constrained heat maps where no data spillage is possible. And what we can see is that how these temperatures kind of differ. For example, if a sensor is put on a windowsill, let's say, it's going to have substantially different readings when compared to some other sensor in the same room, right? And we can see this because we have these high granularity heat maps available for us. Now, the second problem is what I call capturing the flux of data coming in. This is a video capture from our colleagues at Newcastle Urban Sciences Lab, where we have this flux of data coming in for a bunch of their sensors. And if they have a bunch of, and if they have over 300 sensors like we do in our building, there's a lot of data coming in every few seconds. And you want to capture the rate at which the data is arriving on your platform, right? But with having simple heat maps or charts, it's quite difficult to do so. Therefore, our approach was to make use of an analogy or a metaphor, right? We want to see the rate at which the data is arriving. So a good metaphor would be the rate at which fireflies are blinking, or lightning strikes happening, or puddles of water forming due to rain, right? You can see the rate at which something is changing or something is happening, and we wanted to visualize in a building context. So what we chose to do was to draw these ripples of rain on our floor plans that would enable us to understand the rate at which the change is happening in our heat maps. And here's the two applications that we made. So it's called the first one is called the rain app, where we have our heat map, and then we draw these puddles over it, representing new data coming in. And with new data coming in, that heat map is constantly being updated in real time, right? So if CO2 values start to rise in one of the rooms, right, you'd see the effect of that in real time, because first you see a splash, and then you see how color values have slightly changed in that room. Now, the second application is called Splash, and it's basically rain just without the heat map. It's a really useful tool for maintenance to see if all our sensors are still alive and kicking. Now, some of the benefits of having this low latency synchronous platform is that it enables us to see what's happening in the building without actually having to be in it, right? So let's say here we have a real long corridor with a bunch of sensors mounted on ceiling, right? And without having to go there, or without having a camera installed there, you can see that there is a bunch of people crossing the corridor back and forth. And this is a very privacy-preserving measure in terms of being able to see what's going on in the building without having to look at the people that are standing there or walking there. And this is one of the benefits of having this really low, really fast platform. I believe this summarizes what we have presented to you, and I'd like to thank you for listening, and please feel free to reach out and ask any more questions. Thanks so much for listening.